demand. So in the early stages of the development of the mobile phone, we just want a way for talk on phone when we not home, when we on the move. That was all that people want, right? You got a phone and you talk on it and you're not home. You're moving around with this phone and people could reach it anyway. And that was a revolution, right? That was a big, big deal. Then internet come about in the 90s now, and people want to now be able to browse the email or load a web page on the phone. So there was an expectation for being able to use the internet. When you start using the internet now for data, right? For data, which is email and so on, and loading web pages, then there was a demand for audio and video, right? And that's how you end up with 3G now, right? So people are able to get audio and video. I remember the first time I watched a YouTube video on my phone was a big, big deal. And this is not long ago. This is 2016, 17, right? This was this recent that you did start browsing YouTube whilst you're on the road. And that was the 3G. And then the demand start to increase, right? You start getting IoT, right? Start getting high definition streaming. You start getting media, people using devices for media, right? Wherever part you're located, you got different people that want to stream and see what's going on. And those were 4G. Now the demands come for 4G. Now with 5G, you got even more demands now, right? And you got things like augmented reality. Anybody knows augmented reality? Anybody could explain to the class quickly what's or augmented reality, virtual reality, and if anybody knows what's extended reality? Yes, this is the first time I see the term extended reality. Anybody, just know, quick as well. What's the difference between them?
Sir, I think augmented reality is where you use, or currently they have goggles which would overlay certain features and so on, so that your everyday task would be assisted in real time using these
Okay.
special
And
devices.
virtual and virtual
Virtual
reality.
is when you're fully immersed into the environment, so the entire environment is virtual. It has no physical aspect in it, really.
Which one is Pokemon Go?
I think that's augmented. Yeah.
Okay. Yeah, yeah. So the entire landscape of things changing, right? I think of it like like troubleshooting, right? I mean, as of now, if we got troubleshoot something with a customer, right? You they could video call you and and use one hand and point at the cables and the kind of thing, right? With augmented reality, they could put on a glass or extended reality. I'm sure which one of them. They could put on a glass and you got a glass and y'all network together. And as they walk around the room, it's like you walking around and seeing everything, and you could direct them what to do, and it make things better. Or if you're shopping, you're able to try on clothes, right? So you do like a scan of view of your entire body and just transport it into the space, right? You can make people lazy, of course, but it's a whole changing thing. They got a lot of revolutions they could use. So they got people that are trying to do augmented reality for shopping, try and break into the retail space for it. But the thing is, technology and the requirements for technology changing. So other things that you got now is remote control of robots, right? And in the healthcare industry, right? And then of course you got digital learning, and the demand's greatly increasing, right? The demand's greatly increasing. Right. And then of course we got AI, right? Which embedded in everything that we do. In every industry. The other day we went to a symposium where we look at the use of AI and digitalization for occupational safety and health. What they're looking for do is put cameras inside a room or in any space and detect whether people wearing the PPE or some protective equipment. Look at if people saying no with poor posture and is who there is Ryan. So is Ryan to demonstrate for them. You got a video, Ryan? You can show you. You can share your screen and show you. Hey, Ryan, you can hear me? Naging there. Sleep. Yeah, so in every single field, you got um you got applications for these. So technology changing and the demand's changing. And it's basically three things people gonna demand to enable these technologies, right? They want it to get low latency, higher bandwidth, right? And higher mobility. Now this one is important. And of course, reduce energy usage. Reduce energy usage. So low latency means if the time is 5 milliseconds, your round trip time, you want to reduce this even further. Higher bandwidth, of course. If we're getting 100 megabits per second now in 4G, you want increase this probably to 1 gigabits per second. Higher mobility now. If you're moving, right? If you're moving at 10 miles per km per hour, right? Then you might be able to get speeds of 40 megabits per second. But then if you're moving at 50 km per hour, then you might just get speeds of 10 megabits per second. So you want to increase mobility. That's if you could move faster and still operate at a sufficiently higher bandwidth. Remember, when you're moving fast, you're changing from tower to tower, right? Especially with smaller cells. So higher mobility is an issue. And the other thing they want, of course, they want to look at ways that you could reduce energy, right? Always reduce energy. Because if you're increasing your bandwidth, you don't want to see an accompanying or a correlation with the bandwidth that you're using and the amount of energy that you're using, right? So you don't want a straight line increase, a 10% increase in bandwidth, a 10% increase in energy. You want to change, right? So, so those are these days, so now it's challenges that you get. So for 5G now, which the development started in 2018. This is when I doing around when I doing the MSc 5G research was a big thing. Right now, 6G research start and they're looking at how they could get it deployed. So some of the technologies that we start in Wi-Fi first, you should be familiar with some of these. Is MIMO, massive multiple input, multiple output antennas, millimeter waves, they are higher frequency. Instead of CDMA, they get OFDMA, and they got other ones, NOMA. The bandwidth now you start go up higher. Instead of 100 megahertz of bandwidth, you get in 30 gigahertz to 300 gigahertz of bandwidth, which is plenty, right? And the applications, of course, they increasing. And if you're going to be controlling remote devices, right, or remote robots, especially in the healthcare industry, then you gotta go low latency. You don't want to move do something with your hand and then it move like 10 seconds later or even 2 seconds later. So you gotta ensure that you get sufficient latency, low latency, right? So those the lady groundwork as to what you got a great demand, right? And the nature of industry and people requirements changing and they want to use this over mobile. They got a next concept as well to what people proposing for move away from Wi-Fi. So when you're accustomed to, let's say you got a home or you got a conference hall here, right? Is that you got a router here and you got this is a fiber optic cable that going back to the provider, going to the provider, right? And you got a router. And then you distribute the service, right, to different access points. You go to some switch, and then you go to different access points. And what you use to distribute the service, to distribute the internet, you use Wi-Fi, right? Now they got another model. They call it radio over light, right? So in this model now, what you do is that you got, what you say, you got a tower here, right, which is the E node B. So you got E node B there. And then you got like a small E node B inside the building, right? H and B. So this is a E node B, and this is a H and B. A home E node B, right? A home E node B. Right? Good. And then, right, the RF from this, you carry it, and you don't put it new devices inside. You carry the RF cable, right? And you just pass them to what? You pass them to the light bulbs inside, right? So you got your 5G, right? or even 4G, E node B, you come to a home E node B. So this is a little cell now, right? Inside this house is a cell. And you distribute the signal now with access points. You kill the AP industry. You distribute the service, right, over these light bulbs, right? So you modulate the light itself and transfer the energy over there. And so you're connecting to the light bulb, right? So there's radio over light.
There's more energy though, it seems.
I hear though.
It might use more energy as well.
Yeah, let me see if I find this Professor. What's my name? Internet radio of Internet of Radio Light. Fancy thing. See how? Yeah, so you see, you get a home E node B, and then look what you're doing. You carry it in and you distribute it over your light stems. Intelligent light roses, right? So this is the vision. And the professor that's working on this, right? This one is going to teach me, John Cosmos, right? Was a bad man. He's working on some proper things. You know, like when you go through them airport, you just gotta take off your belt and your computer and them thing and pass it through a scanner and so. Well, he looking for one. He researches for eliminate this completely. Internet range overlay, tactile internet, right? I tell you, it's tactile internet. So this is the next so there's different research areas that he got. So it's ultra low latency and extremely high availability. Well, this is why you gotta get 5G, and again enable humans and machines to interact with the environment. So it's pretty interesting. But this radio overlight one was a bad one. Let me go back and see it again. But if I can design quick. Yeah, see, you got your home E node B. And then they're connected to some kind of gateway inside your home, and then you distribute the service, right? The different lights. So you don't have to put additional access points and so. You just pay for a mobile data plan from the provider them. You get his device and then you distribute it inside it. So that's what he did working on. Now you notice you got some buzzwords, NFP, and SDN. I gotta explain what's these because these are important in 5G, right? The entire industry change, right? The entire industry change. All right, so they need a lot of spectrum. Now you can see the word Cloud RAN being used, Cloud Radio Access Network. So I can explain to you was this the air interfaces, of course, from the E node B to the from the devices to the E node B. But instead of the UU interface that we got in 4G, we got the NX interface. Now this X could be 1, 2, 3, 4. It all depends, right? The next thing, so these are some of the things that 5G gonna got. The frequency spectrum needs, they're gonna need a lot of spectrum. For the air interface, they're gonna define this as the NX interface, and we can see it in a diagram. You need massive system capacity. I explained for you why. Very high data rates, right? And not just peak data rate. So let me explain. There's something else too. So oftentimes you might see, right, that a Wi-Fi access point provides 1 gigabits per second. But the thing is with this definition, this is in ideal situations, right? Not real life. Because the farther away you move from the AP, bandwidth reduces. Right, so that's one. The farther away you move from the, no, well, actually, the more APs that are installed, the more interference you have. So then bandwidth reduces, right? Bandwidth reduces. So in practical, in real life, instead of 1 gigabits per second, you might more likely get 300 megabits per second. I always have the bandwidth. If I have to find, say, doing a gig, 1 gig per second, it's 500 megabits per second for me. The other thing is the more persons connected, the more competition for resources and bandwidth reduces, right? So theoretically, you get like 300 megabits per second. So what it's saying here, right, is that more important capability is the data rate that can actually be provided under real life conditions. It don't matter what the peak data rate. The peak data rate might be 10 gigabits per second or something, but the actual data rate that you get might be less. So in urban and suburban areas, 100 megabits per second, and some other areas you might get 10 megabits per second per device, right? It all depends. You need very low latency, of course, if you want to enable things like the tactile internet. So 1 millisecond or less. If you look at mean latency right now, mean latency for go out to Google is 102 milliseconds, and this might be too much for some communication. 102 milliseconds means it takes me 50 milliseconds to go to Google and 50 milliseconds for Google to come back, right? And then ultra high reliability and availability. So service gotta be available, right, and reliable. So you got redundancy built into it. All right. So we take a quick 4 minutes break, and then we can continue and talk about these. Any questions? All right, good, good. All right, let's continue. Now I want to show you something, right? This is the thing with academia, right? Now we're now talking about 5G, right? Didn't even deploy properly in Guyana yet. You see what people doing? They're researching reconfigurable intelligent surfaces for 6G systems, right? Now, let me explain to you what we're going on, right? It's important that we think this, guys. I want you to understand and get an appreciation for the academic process, right? I understand how this entire thing structured. Final year students now, they get an appreciation for academia as a whole, right? That's a very misunderstood, especially at UG and Guyana. So 5G networks are now being rolled out, right? And one of the key technologies is massive multiple input, multiple output systems, in which band? The sub 6 gigahertz band. The challenge is the millimeter wave band was the one that they wanted to use, right? That was originally envisioned as one of the bands, right? But what challenges to get? Because it's high frequency, we know this is second year telecoms. If you propagate RF signals at high frequency, they're going free space path loss going to be very high, right? They're going to quickly attenuate. So you don't get far with the line of sight, right? You don't get far. So you get severe path loss and sensitivity to blockages, right? But however, right, I just explained to you at the start in what so many technologies that we want to use with 5G. Now look, immersive virtual reality, hi-fi, high fidelity, holographic projections, digital twins. I don't even know what's digital twins, right? Connected robotics and autonomous systems, intelligent transportation system, brain computer interfaces. I'd laying a case for you at the beginning of the class that with every evolution of mobile technology comes an increase in demand of things that we could do, right? The imagination, you let imagination run wild, right? Don't whatever we could do now that's what we possibly and we design a system for it. We continuously looking for ways to improve. Let me see what's digital twins.
Right, when you
Is a virtual representation.
yeah.
Yeah, sorry, what are you saying?
No, it's when you model actual machines.
What was digital twins? Right.
There you
So a virtual representation of an object to reflect a physical object accurately. Good. There's one immersive virtual reality. Well, it is similar to the one that we got. But the thing is, you see, they're already thinking, right? They're already thinking. So if you go back to the beginning, this 6G here, notice how the applications keep changing. First was just voice calls and messages. Then you start moving up to you start increasing in terms of the things that we want, right? Now they get even more fancy, right? And the problem is, right, how we know that in order to move up, we gotta get more bandwidth, right? Shannon's law, right? Basic Shannon's law. Your capacity that you get proportional to the bandwidth. So you gotta use higher bandwidths. Now the problem is at these higher bandwidths, you're getting severe path loss, you're getting blockages, you're getting limited coverage. You just can't simply increase the amount of power, right? Because there's a challenge, right? Power is limited. So in this research now, what they're looking at reconfigurable intelligent surfaces. They're saying, look, this signal gonna hit some kind of object, right? This signal gonna hit some kind of object. So we send out a transmission from here, and it's gonna hit this wall. All right, good. Now this wall now gonna prevent it from going how far it's supposed to. Let me say somewhere like this, right? So what they're gonna do instead, right, is that the surface that they're gonna hit. Let me just visualizing, right? I know the full paper and everything in. Is that let me get this material now, right? That we can start putting on walls, right? This special kind of material that we can put on walls. But this material is such that when signals impinge on it, right, it can automatically adjust itself and change the phase, right? So that the signal gets reflected off of it now, gonna line back and represent the original signal that get transmitted. So it's reconfigurable and it's an intelligent surface. So there's not a device like a router or something like that, right? They're actually looking at the walls themselves. The walls is the problem, let me change the wall. If the wall blocking transmission, let me change the wall now. So when you signal now, right, make the walls an electronic, right? And then sell them. Market it as a product and then sell it, right? So walls, ceiling, doors, and so on, you're gonna reflect the RF, right? So you could create a virtual line of sight, right? So it's like like a digital repeater system. Collect the signal, right? You do your error correction coding and so on, and then you modulate, you recreate the signal, and then you send it off back, right? But remember, it's not gonna be an active device, right? It's not gonna be really an active device. As if you could get it to operate passive, then there's even better. So is a surface that can adjust the phase, right, for the signal that impinge on it and create a virtual line of sight. And there's research that ongoing, right? It's research that's ongoing, and you already got people, right, that doing a lot of research on 6G. You look at your references, so you got people that's looking at it. So the development keeps going. You got a problem, what solution we got around it? And these is research problems, right? It's not really application in the sense that the technology exists and how best we could fit it to this environment. So an implementation challenge would be like, all right, you got this village and it's located X amount of miles away from this place. What is best backhaul we gotta use? We use satellite or we use microwave, and what Wi-Fi we use. And then it comes down to cost and what supply you got and the kind of thing, right? But let's say so now is actually heavy technical thing to try and create something new that never went before to solve this problem. So I just want to find out here. All right, so 5G now, you got a radio access network, and they define some new terms. They got GNBs and ENBs, right? eNodeBs is the same ones from 4G and ENBs. And the interface between the two, between an eNodeB and a GNB, is going to be the XN interface. And the interfaces between, right, the eNodeBs or the GNBs and the 5G core network, right? The 5G core network. NR means new ratio, right? Is the N interfaces, right? So we can see a number of them. They got another diagram later on that you can see. But before that, let me explain the concept of Cloud RAN to you, right? What's Cloud RAN? So in 4G, you learn that you got the eNodeBs, right? Good. And then you probably got some data center. So you got eNodeBs, and these eNodeBs now are then connected to the transmission network, right? These connected to the transmission network. I'm gonna drop a couple eNodeBs there. And then they go back now to the data center. So I just abstract the data center. So this is your transmission network. Right, and this now is your data center. So this is now going to be your EPC, right? So what's some of the components here? EPC, you got the SGW, you got the PGW, you got the HSS and the MLE, right? Good. And then here now you got your eNodeB. So you got your different eNodeBs here. Now I'll tell you something from 2015 to 2000 and what do you think name? So in NDMA, right? We got we had a container, right? And it got a couple of racks, right? So it had 3 racks on this one side. So there's one side of the container and inside the aisle, and then you got 3 racks over this one side. Right? And the original 4G network that we had. Good. Now half of this rack, right? Half of this rack was for the UGW. Right? And the UGW was the SGW plus the PGW. Then half of this rack was for the HSS, right? And this is a 42U rack. You remember it was U, right? It's a measurement of height. And half of this rack now, right, was for the USM, which was like the MNE, right? So this was what we had, a whole half side for all of these different functions. We had some other stuff over this side too. But so this was in 2016. So these was blade circles, right? Blade circles. In 2020, when they upgrade their system, right? When they upgrade their system, they replace all of them with servers. And all of these things, right? These three different racks fit in one rack, right? All of these here fit in one rack, right? And how they do that? Instead of getting what you call an appliance, right? They install, right? They virtualize them. They virtualize the UGW, the HSS, and the USN, right? So before you had a piece of hardware, a piece of specialized hardware. So this was like it, right? So this was just like the chassis, right? This was the chassis. Now inside the chassis now, you got slots, and then you got different boards. So just like a router, and then you got different boards. So you got one board here, you got next board here, you got next board here, and so on, right? And this could be hot standby boards and so on, and this was your UGW. So this was this entire hardware. And then you had a different hardware, you know, for the HSS and a different hardware for the USN. So there was appliances, right? Because you got a special function that they perform, right? Which is like the SGW, PGW, HSS, USN, and so on. And then you install them on this physical hardware, right? And you couldn't take a board on this UGW and put it on a board in this HSS. You couldn't take a board on the HSS and put it in the USN because each one of them was their own person, right? Each one of them they'd specialize for some function, right? So it was an
Sir, so this
appliance.
was like the hypervisor.
No, but that's the thing. This wasn't like the hypervisor. This was it installed on the hardware, right? It
Oh,
installed on the hardware itself, right? So it was like a computer. So it's one computer, and all this computer doing is UGW work, and all this computer doing is HSS work, and all this computer doing is USN work, right? But so that was 2016. In 2018, then, right, then what they do, they then provide this kind of setup, a chassis and then got the cards inside, right? What they do is that they give you a set of servers, right? And all the servers was like the same for them, right? So it was a RH, so it was a Huawei RH228 something. I'm gonna load this up here. See if we get a picture. Yeah. So they give a bunch of servers like this, right? A physical servers. So all of them look like this here. So let me see if I find Huawei US. Yeah. So this is how it used to look like before, right? You see this picture here? So this was its own hardware, right? So it had the big chassis and then you had the cars in the inside. So one was like for the USN. So this was the old USN. You see how it there? A big, right? This thing is half a rack. And then you got the different boards them that the inside. And so that was the old model. In 2018 now, you know what they do? They just give you a bunch of these servers. Right? They give you a bunch of these servers, and then they had their own hypervisor over it. And then the UGW, right, become the EUGW, right? UGW become EUGW. The USN becomes EUSN, right? The HSS becomes EHSS. And all of these now, right, were applications. You know, like how you install Microsoft Word, right? All of these ASML was like Microsoft Word. It was an application that you install on the server, right? So you got the hypervisor layer. So Huawei, they hypervisors, they use Fusion Cloud. That's the technology that they just use, right? This is their virtualization technology. And then they install Microsoft Word and well, EUSN, EHSS, and so on. All three of these racks get replaced with one rack. So it's very, very efficient. And they're doing the same function, right? But so this was the evolution. This is 2016, and this is now next evolution, 2020. So what happening with Cloud Run now, right? What happening with Cloud Run? Let me consider back this party, right? Let me look back at this party, you know. You got E node B, E node B, E node B, E node B. Now let me set to this one over here, right? Hold on, I'm gonna show you this thing. So on real life data, so you can see what we're getting. All right. All right, cool. So look at this here now, right? This is V different towards them. Each one of these is an node B, right? And this is the bandwidth that they're using, right? This is the bandwidth that they're using. Now you see this one site A, so 3 megabits down, 15 megabits. Up here hardly doing anything. 3 megabits down, 21. Up here hardly doing anything, right? But you see this one here now, he probably overloaded. NFMU, he probably overloaded, but it's not a fixed BBU we put at the site, right? It's not a fixed hardware we put at the site. If he load up, this one hardly being used, this one hardly being used, this one hardly being used. So in 5G now, because they want to save on energy, you see what's going on here? In 2016, look in the EPC. This is in the LTE core, right? You got separate appliances for each devices. Then in 2020, we get one rack, we put physical servers, and right, and we install the applications on them, right? We install the applications on them. So the question is why we can't do the same thing with the radio access network part. Why we can't take these eNode Bs and put them inside the data center, right? Why we can't put them inside the data center. And that's exactly what they do, right? They use a cloud model, right? They use a cloud model. So what happened now? There's the old eNode B. What they're gonna do now, right? So if you remember, we had the antenna connected to the RRU. The RRU with the fiber optic cable using the CPRI, now connected to the UPPV board, right? And the UPPV board is a part of the BBU, right? Which is the eNode B. And then this go out with fiber optic cable to the router, right? The PE router. And then he go out with fiber optic cable, right, to the rest of the transmission network. And then he go out with fiber optic cable, eventually back to the Evolve packet core. So you had all of these layers here, so, right? The Evolve packet core connected via fiber optic cable, transmission network with a fiber optic cable to PE router, with a fiber optic cable to the eNode B, and then the eNode B via fiber optic cable to the RRU, and the RRU to the antenna, right? Now, all of these here, right? All of this part is at the LTE site, right? At the tower. And this part here now, right? This part here now is inside your data center where you use virtualization. So in 5G now, right? For 5G, for Cloud Run, right? For Cloud Run, what you do is that you got your antenna and you got your RRU, and you got your fiber optic cable, then you got your transmission network, then you got your fiber optic cable, and then you got your core network. And this includes, right, includes the eNode B. This includes the eNode B, or your GNB, which is depending on whichever ones you got. So this now, right, this is all you got at the site, at the LTE site. The problem is, right, is that this antenna, this RRU, right, he doing RF. So how is it that you're getting RF, right? From antenna to RRU, to fiber optic cable to transmission network, come back to fiber optic cable, back to the core. And the question is, you gotta use the radio over light, right? It's radio over light. So you got your eNode Bs or your BBUs inside the data center, and then they could control multiple sites. So instead of the previous model that we got now, we got a bunch of eNode Bs or GNBs installed inside the here. And they could serve as different they could serve as different sites, right? So if this site now, this is me NFMU, and he had 50% utilization, and this now is me conference center site, and he had 20% utilization, and he now UG is at 30% utilization, and so on. This is Police Sports Complex. He had 10% utilization, and they say some maybe transport. He had 80% utilization. We find out in the previous model, each side got beyond, each side got power up, each side take up a lot of space. and overall energy usage, right? Overall energy usage might be, I just put in some numbers here, so right, might be 15 kilowatt, right? And overall capex, right? Capex might be 10 million. Capex means the initial investment in equipment. So this is with the old model, right? This is with the old model. With the newer model now, your overall energy usage will decrease. You might just get 7 kilowatts now, right? And your overall capex will be very, very low, right? It'll be like 3 million probably. And this is the new model. And you get the advantages for it. So now, not only, right, you virtualize the core, you also virtualize the radio access part of it, right? You virtualize the radio access part of it, right? So these now come inside of the core network and use RF overlight, modulate the RF signals directly over the fiber optic cable to get out to the customers. Now the thing is, you no longer got LTE sites, 5G. Even the little base station is short range. Let me get with it. Yeah, so instead of a big tower, the idea is that they could embed them in stuff like this. Like, right? Look at this image here. Let's see if I get it better. Yeah, you see, look, this is a big tower, and then you got your antennas all over it. What you start do now is that you disguise them. You put it in a street light. You put it in one of them traffic camera pole or something, and you just get your little antenna here that's gonna distribute to a small cell. It think a big, it think a high power, and those your cell there, right? So you got macro cells and you got micro cells. So people who they're close to it, right? People who they're close to it now can get higher bandwidth. As you move away now, you might connect to one of the big tower, right? So that's the idea behind it. You got femtocell, picocell, microcell, and macro cell, right? And then you got different parameters and things for them. Make a note of this, say son included in your lecture notes. All right. Now let me look at the just want to show you what the 5G core network look like. Before that, let me take a quick break and we can finish off. Just like a 2 minutes break, and then we're gonna close. Right? We'll be back in a 2 minutes.
Sorry, yeah, break now, right?
Yeah, not long, just a 2 minutes.
Okay. I just think kick out and come back in, that's why.
All right, let me close off now. Yeah, so before we look at this, before we go to this, let me explain to you software-defined networks. Right. So software-defined network now. In all networks, right? In all networks, you gotta say there's a router, right? You got a router. And on this router, right, you configure OSPF, right? And SDP, DHCP, NAT, BGP, static routes. All these are the things that you learn, right? And on this router, right, control plane and the data plane, right, are on this same device, right? On this same device. And decisions made are localized. So this router, if it got choice between two different paths, right, based on the calculations that the router runs, he selects whichever path is optimal to him from his perspective, right? You don't concern with what this router think is best for him. He concerned with what the router after this router thinks is best for him, right? He only looked from how far he could see, make a decision, and he concerned with any other devices. Very, very selfish. Now, this is very, very suboptimal, right? Very, very suboptimal. Because think of it, if we could coordinate traffic lights around town, then we could control traffic flow, right? You could cause some of the lights to go for longer so that you could push more traffic into an area that's less congested, and then build up a queue in some areas that ain't as congested as well. And it could overall manage to take out a view of all the traffic lights them, right? Of all the traffic lights them and the build up of traffic inside of the city. So it's the same thing with software-defined network, right? What you got is what you call a software, a controller, right? You got a controller. And then you got switches or different devices. But and on top of the software-defined controller now, you got your different applications, right? That control your routing protocol. So you got your network here. And then you got different devices that connect to this network, right? And then the network connected to the software-defined controller. So these days, now is your applications, right? So you could write an application, and then you got a northbound interface. And here you got your software-defined controller. Software-defined controller. And then here you got your southbound interface, you call it, right? You got your southbound interface. And this is your network now. Just like you got your switches and everything like that. This is your network now. And then here you got your end devices, right? You got your end devices, which we don't call routers or switches. You just call them network devices. You got your forwarding devices. So what happened now is that each of these devices just tell the software-defined controller the current state of the network, right? The software-defined controller now, he running all of the calculations. He doing the OSPF, he doing the DHCP, he doing the NAT, he doing the DHCP, BGP, and so on. You got applications here that you could write for control traffic flows however we want, right? So we could create our own rules and write a little Python code at the top here now, and we push it on with a northbound interface. And the northbound interface is usually the REST interface, right? It's usually the REST interface. So your applications, you got now let me say the application say any traffic that gotta go from Daniel to Lemuel, pass it through Sohail first. That's what we can write in this code. Now with the REST interface, now REST API interface, now they're gonna communicate with the software-defined controller. The software-defined controller now getting information from these devices now, how far Daniel there and how far Lemuel there. And he now gonna push instructions to these devices that say, if Daniel want to get to Lemuel, send it through Sohail. Right? Now, normally, how to configure devices now, right? You normally know this adjust the cost on your links for control routing, right? Or spanning tree, you set the root priority or the kind of thing. And that happening on a per device basis. And then all these devices got exchanges information with each other via like PPDUs and so on. With software-defined networking, he got a vision of the overall infrastructure, all the different devices, and he pushing this instruction to these devices. And they don't make any decisions. Their role is only to forward information. And because they ain't gonna make decisions, right? Because they ain't gonna make decisions now, then they could be less costly. You gotta get expensive CPU and so on in them in order to make all these decisions. Their job is just to forward traffic. All the intelligence is inside of the data center, very centralized, just like with the 5G network now. All of the decisions is happening inside the data center. You got your EPC, right? You got your EUGW, your EUSN, your MME, and all these node Bs inside of the data center. So what industry moving towards is putting all the heavy computation for happening inside of the data center, right? So that the devices that are at the end now, they only got push packets, right? They only got push packets. So this model of software-defined network, is the model that 5G uses, right? And this is what the overall architecture look like. You got some names here that we can talk about tomorrow night, not tonight. UDR, AF, PCF, UDM, AUSF, a whole set of them, like how we had UGW, MME, and so on. You got all of these devices, right? And look at the interfaces that these devices use to communicate. The N1, N2. Remember, I tell you NX, you got N1, N2, N3, N4, N5, N9, and so on interfaces they use to connect. And each one of these now just communicates with each other through some RESTful interface, right? Through some RESTful interface, and they got names for them here. So NAF, NPCF, and so on. So this is the model now for the 5G core network. But it uses what happened with cloud data centers, right? The whole concept of virtualization is what it uses, right? Tomorrow we can talk a little bit about the services-based architecture, and we go through a couple other stuff. But that's how far I want to stop for tonight, right? So tomorrow we can think, and I want to talk a little bit about quantum communications, and just introduce you to two more research topics, like how we talk about ratio for light tonight and reconfigurable intelligence services. Any questions, anybody?
Sir, don't mind the meter.
No, me no. Here, I get everybody coursework grade before exam next week Tuesday. Right? By Monday, you're gonna.
All right, good.
Good. Right. All right, good. See. All right, that's it for tonight. Thanks for staying back. Tomorrow night, to I'm letting OCR because I normally stay in UG and stay in work there and then teach and then left. But then I'll do it tomorrow. So once I'm done, then I'll be home and I'll keep you in the loop to let you know what time we start in class, right?
All right, sir. Travel safe.
Good. All right. No, I didn't home now. Yeah. All right, good. See you later.
Yeah.